All right, so this is 7.4, the second part of it. I'm going to go ahead and tell you, you're not going to use this very much. We're going to talk about it and you're going to have some homework questions on it, but I do not even remember ever seeing a surface area problem on the AP exam. Not to say that it won't. I'm just saying I've never seen one and never heard of one. But we will talk about it. It's not that much unlike your length of the curves. And it's something that you may end up having to do at some point along the way. All right, so consider a curve rotated around about the x-axis. So if this curve, we're going to take, what we did was the same way we did in 7.2, where we did the area between two curves. Then we took a curve and rotated it around and made a solid. Now we're going to take the length of this curve, rotate it around, and it's going to be the surface area of that solid. So that's what we're finding here. So you're going to still end up using the exact same thing you did in 7.2 or 7.4 part 1, but then we're going to use that length and a radius to actually find what the whole thing is. It's going to be very, very similar to our shell method, really. I mean, that's really what it is. It's going to be a shell method, and it's only going to be a single shell. So the surface area of this band is going to be 2 pi r times ds, which is the length of the small length of the little segment there. So the radius is the y value of the function. So the whole area is going to be given by the integral from a to b of 2 pi y ds. Now, this is the same ds that we had in the length of the curve formula. So when we put that in there, what happens is the formula now becomes s equals the integral from a to b of 2 pi y times the square root of 1 plus dy dx squared dx. Remembering that this part right here is what? The length of the entire curve, and this length right here is the circumference as we rotate that thing around y. Now the reason the y is here is because as we move up and down this curve, what's going to happen? Well, my y value is going to change. That's why we can't just say it's a certain number. And this only works for Cartesian. You get into polar, it's completely different. We'll talk about that later, maybe. I don't know if we'll talk about surface area. Now, to rotate about the y-axis, we're just going to reverse the x and y's in the formula. That's all we do. So x, x, y, y. That would change. And guys, you're not going to see in any test, any problem, anything where we're going to rotate and find the surface area around something other than the x or the y-axis. I'll just go ahead and tell you. If we do, if there is one of those problems, let me know, because I did not mean to put it on there. There is just a time where it's getting too complicated and it's not really a benefit. All right, so for example, let's rotate this thing around the y-axis. And we're going to find a cone is what we end up with here. So this equation is y equals 4/3 x plus 4. And when we rotate that around, we're going to get the top part of the cone. We're not getting the volume, so don't go calculating the volume of this thing. We're only looking for what's called the lateral area of this thing. Only the part up here that's turned. Of course, we got the area of a circle on the bottom. So y minus 4 equals negative 4/3 x. We've got to solve for x since we're rotating around the y-axis. So dx dy is negative 3/4. So rotating around this way, rotating around the y-axis, we're taking small pieces here. Remember, our radius, we're rotating around this, so this is what we have to integrate with respect to. Sorry, this is what we have to integrate with respect to. So we end up with the integral from 0 to 4 of 2 pi times the x value times the square root of 1 plus dx dy squared times dy. And then you would not be expected to try to do that by hand, even though you actually can here. The square of that's going to be 9 over 16. And you have 16 over 16 plus 9 over 16 gives you 25 over 16. That's going to give you 5/4 when you take the square root. And then you can move that and the 2 pi all the way out front. And then you take the antiderivative of this, plug everything in, and you end up with 15 pi. But the biggest thing I want you to focus on is how the setup goes. Setting the thing up. So if you're rotating around the y-axis, you're going to integrate with respect to y. If you're rotating around the x-axis, you're going to integrate with respect to x. All right, so if we take this, rotate it around the x-axis, y is equal to the square root of x. And you probably remember that one. We did that one with the length in the previous section. So we're finding the surface area of that nose cone-ish thing there. So if we're rotating around the x, we're going to integrate with respect to x. So we've got 2 pi y. Y in terms of x, by the way, times the square root of 1 plus dy dx squared dx. All right, so we're going to end up putting the square root of x right here. We're going to take the square root of this, or sorry, the derivative of this, which is going to give us 1 over 2 square roots of x, which is going to go right here to be squared. And they did it with a calculator. So let me write this in real quick just so you can see it. They've already moved the 2 pi out. We're integrating from 0 to 9 times the square root of x times the square root of 1 plus 1 over 2 square roots of x, quantity squared, dx. Remember, this is nothing more than x to the 1/2 and then do the power rule. So you end up with 1/2 x to the negative 1/2. That's where the 1 over 2 square roots of x comes in. So then, of course, you could square that and simplify some things down, combine stuff, but you're going to end up doing this with a calculator anyway. I just don't like this part. Go ahead and find the derivative and plug it in. It's just easier, I think. And you should get the value or the solution, the answer of approximately 117.319. Now, if we rotate this about the x-axis, of course, what figure are we going to get? We're going to get a sphere. And guys, let me tell you this. If you have a problem like this ever on an AP exam, do it the easiest way, unless they specifically tell you to solve it using this method. Find the area of the sphere, put the answer in, and be done with it. the 4/3 pi r cubed thing. Do that. But unless they specifically tell you a way to do it whatever way is easiest. Now I'm going to show you the setup for this, but we're not going to work all the way through it. So then here, if we're rotating around the x-axis, we're going to have 2 pi y in terms of x times the square root of 1 plus dy dx squared dx. Plugging everything in, we're going to have 2 pi times the y, the square root of 1 minus x squared, times the square root of 1 minus the derivative of this squared dx. So you could store the square root of 1 minus x squared as your y. I would much rather you get in the habit of entering it like you're going to graph it. So make y1 that thing. And then you can use the y1 everywhere in here that you want to. I don't like storing as the variables that we use there. You can store it as a letter. That's not bad. Like store it as a. That would be okay. And go from there. I think you can store a function as a. I'll have to check that out. And then it just plugs everything in everywhere. And your solution is approximately 12.566. And, oh, sorry, I did volume. When I did 4/3 pi r cubed, that's the volume. We're doing surface area, and it's 4 pi r squared, sorry. And then when we plug that stuff in, this has a radius of 1. It's 4 pi, which is approximately 12.5663. For those of you guys that caught the mistake up here with me using the volume, good job. If you didn't, well, you need to be a little more familiar with those equations. Catch me when I mess up. And once again, if you happen to use this and store things as x and y, remember to clear those variables when you're done. If you don't, it will mess up calculations down the road. That's one of the reasons why I don't like storing them like this. You can do it if you want to. Just remember, clear them, please. All right, and that's all.